Yeah, I'd like to start the afternoon talk with some add-on, which I wasn't able to cover in the previous one, but I think it's important enough and it fits. It's about dimensions of the corresponding vector spaces, which is something that we should add. So, a short digression on dimensions. For MZV vector spaces. So a priori, we have seen so many relations that it's not even clear whether anything is left over. Right? If suppose maybe there are so many relations among the zetas that we have just rational numbers, and so then what we're doing here is maybe almost a bit. But on the other hand, we know at least one number which is irrational, zeta 3, explicitly, and in fact we know that there are infinitely many linearly independent odd zetas. So that's something I've stated in a weaker form earlier. But so there are certainly things left over, but let's just say, so the experiment that Zagier originally did in the following dimension conjecture. So let's put following. Sorry, you have to figure out. I assume that you. It's autocomplete. So we put a dk as a dimension over Q of the space Q generated by the zetas underscore k. So that's a vector or several arguments, such that the weight, so the sum of all these entries, is equal to a fixed, this k. So that these are two different k's, one with underscore, so that's a vector, and this one with a natural number. And he finding, so for a k equal to 0, 1, 2, 3, 4, 5, 6, 7. Let's do it up to 8, just give as before, an impression. So conjectural basis even. So here we have zeta 0. So, because, well, he doesn't listen anyway. Okay, so, which is minus 1/2, but we could also obviously take 1. Here we have nothing in weight 1. In weight 2, we have zeta 2. So if we want a basis, okay, I should write braces. Here, well, I'll leave out those braces, I think. Zeta 3. Oops. And for 4, we have, just zeta 2 squared, for instance. That is a conjectural basis. Conjectural. Because, we can express everything. So what's the statement is, everything can be expressed in terms of those stated here. Right? So certainly, so the conjectural basis, certainly generators, is okay. And here, zeta 5 and zeta 2 times zeta 3, say. Now it's getting difficult with the space here. So zeta 2 cubed, zeta 3 squared is maybe an interesting basis. For 7, we have zeta 7, zeta 2, zeta 5. And you sort of get a vague idea of what's going on. And the first sort of interesting case that I mentioned before, where something that's not expressed in terms of Riemann zeta is in weight 8, at least conjecturally. So we have zeta 2 to the 4, zeta 2 times zeta 3 squared, for instance, zeta 3 times zeta 5. But then, here it comes, zeta, okay, this is 6, 2. That's another version of it. So that's a conjectural basis for 8. So let's look at the dimensions. So we have dimension, dimension 1, 0, 1, 1, 2, 1. It's tough after a long night. Okay. 2, 2, 3, 4. Okay. Now, that's a sequence that doesn't tell many people so much until they studied a bit closer. Well, some people can actually see if you look at this one and the previous ones where you have a jump, like for instance 2 is equal to those two, the 3 is equal to 2 and 1, and the 4 is equal to 2 and 2. So that is roughly what comes out. So recursive formula, that was the conjectured one, dk equals dk minus 2 plus dk minus 3. And the starting point you give as your starting point, the first 3, 1, 0, 1. So that's, and that has been corroborated, and you may have seen that in terms of power series is a good one. That's the corresponding power series that counts the decays. So you just develop that as a geometric series, and then you see that this comes out. Okay. I mean, the decay is the coefficient of x to the k. Okay, then the upper bound of that has been proven by Goncharov. Well, it had been announced long ago by Goncharov, never really written down, but then together with, in his paper with Deline, it was finally written up. And in the meantime, Terasoma also had found a completely independent proof. So, and it also follows from recent results of Francis Brown. Brown's recent results. So there are now different ways to get to that. But actually, Brown has a stronger theorem, as probably, I guess, all of you have heard many times by now during this activity. Because Hoffman had suggested, okay, with this count, 2 and 3, so you go back by a 2, you go back by a 3, so maybe if we only allow the following, so zeta powers of 2, then powers of, sequences of 2, sequences of 3, then again 2, then a number of 3s. If we only allow sort of expressions having 2s and 3s only, right? 2, 2, 2, 3, 3, 3, then this should be a basis. So, conjectural, a basis, let me write like that. The set of these give a basis of the Q for MGVs. And there is no series. So yeah, I haven't given you the Hoffman basis. I've given you an alternative one. So this one was supposed to be. I gave you that one because that's the first presumable non-Riemann zeta, right? It's not expressed in terms of conjecturally as a product of Riemann zetas. Okay. Okay. Now Brown stated this is indeed this basis. So zeta k1 up to kn, where all the k's are either 2 or 3. This indeed gives a basis in a formal setting, motivic setting. And he's talked about this last week, for instance, and I can't say much about it. So it was just we've seen many relations. Now, how to figure out what a good basis could be, and this rather unlikely basis, it seemed a bit ad hoc, take just 2s and 3s from the combinatorics, and people were a bit iffy whether that really would give a basis, but then Francis believed strongly enough and then finally proved. So that was really breakthrough result.
Can I just ask, so he has multi-zeta values, so for the multi guys, this is a basis?
This is a basis.
And now for the regular ones, it's also...
It's a generating set.
Yeah, because you project multi onto, but then...
Yeah, but you could have many more relations among the real values. We just don't know.
So that's my question. You don't know. You don't know if you can descend.
No, that's always this question is, for instance, zeta 5 irrational.
Yeah.
If you can't rule that out, you're not even sure you're working in a Q vector space with enough generators for your decay. So it's really a question of typically of transcendence results, and there's just nothing else. So we always are in this business. So the detour is via this motivic setting where you have much more rigidity, and there you can prove the thing. The formal setting, motivic setting, that's usually what you're trying to do. Okay, let's... Now, the title of the talk was double zeta values. So let me now come to that. And modular forms, I abbreviate. So we recall double zeta values are zeta AB, simply some, now maybe this time I get it right, k to the m to the a, n to the b, where n is greater n, and greater 0, obviously. And they are, as we've seen, reducible if a plus b is odd. So less interesting. Also, we study we can reduce, by experience, sort of to weight-graded pieces of relations. Relations only. All the relations that we know decompose into weight-graded bits. And also modular products. Often, and here I can slightly correct the coefficient in the equation that I gave earlier. So I gave you zeta k minus 1, 1 in terms of zeta k and products. But the coefficient that I checked it for k equals 3, where it happens to be the same. It's k minus 1 over 2. So that's, in case you want to check, the ones that I've given were not correct. So k minus 1 over 2 plus, and it was minus 1/2 the sum of all the products, zeta a, k minus a, for the odd. No, that was for any, sorry, that was for yeah, let me take the second half. Okay, what about dimensions in this case? Well, we ask again, Xavier. Already in the early 90s, he checked this. So for a fixed, so we'll do that in the following fixed weight k, typically. We have following conjecture. The dimension of zeta j k minus j, where here we'd have all the convergent ones, meaning 2 less than or equal k less than or equal j less than or equal k minus 1 over q, is we have one simple part, that's k minus 1 over 2. And here the ceiling function just gives the largest integer less than or equal to this one, minus, and now comes a strange looking thing, so there's a 0 for k less than 12 and k, and also for k odd, and it is k over 12 ceiling function minus, we take away 1 if k is congruent to mod 12. So it's really a very strange looking thing. So that's Kronecker delta. So it's 1 if k is congruent to 2. So this is, of course, 1 if k is congruent to mod 12. That's the shorthand, and 0 otherwise. So this is for k even and greater 12. Greater equal to 12. So that's a nice dimension formula if you know how to interpret it. And the way to interpret it is, this is exactly the dimension of the space of cusp forms for SL2Z. Certain modular forms, I'm going to say more about this since it's supposed to be very pedagogical, so I'll say a few words about modular forms as well, very basic. Okay, but whatever, so some interesting modular forms, and in fact most of them come in. So it's a very natural dimension in principle.
So, these are relations that are not typically expected?
A priori no, but they are now we now try to interpret them typically, or somehow find a good way to interpret them, and there are approaches which I hope to indicate.
How does that match with the prediction?
How does
How does that match with
that's a different. So here it was all the depth. Here is fixed depth.
Oh, sorry, yeah.
Fixed depth and weight.
Yeah.
And there it was all the depth and
It's all there.
allowed. So it's slightly different. Okay, so that is. And Goncharov and Zagi independently showed that the upper bound holds. So just like in the previous case with Goncharov and Parasoma, they showed that there's okay, not much. So there is at least evidence that there is a good chance of a relationship. Okay, and so for k even, do expect a relation with modular forms of double zeta values and modular forms, cusp forms. So for k odd, since there is 0, you wouldn't expect it. And surprise, Zagi told me that in his proof of Brown's the identity that was crucial for Brown's proof of Hoffmann's conjecture, he used actually implicitly something like a relation even for the odd case. But so I'm not going to talk about it. I haven't understood that at all. So and the aim here is now to make this explicit. There are different ways to get that. We'll see how far we go. And as byproducts, we get new relations among double zeta values. Of course, new always says it's not known to be a consequence of the ones that we expect to generate everything. So let's first maybe take or maybe an example. Yes. What do we expect? For instance, I indicated one similar one, refined sum formula. We've seen that if we take all the double zetas of a fixed weight, then this is zeta k. Now let's take only half of them, take the even ones. Then this gives you 3/4 of that, and therefore if you take odd ones, you'll get 1/4. So it occurs in a ratio 3:1. That seemed surprising to us, and recently I've seen that Hoffman found that this already can be somehow read off from what Euler did. So when I say we, so this is Euler, and we restated that in joint work with Kaneko Zagier about, and it's about this paper mostly what I'm going to talk about today.
What was it like to talk to Euler?
Oh, it was great.
You are seeing
This is even. I think. So in the following, so everything is now k even. So because k odd, we thought at the time that has not much bearing. So everything's stated now for k even. Yeah, thank you. Okay. And so we mentioned earlier the double shuffle relations. So how do they look like in depth 2? So the first one is the easy one, zeta nn plus zeta nn plus, or let's write it together, it's zeta m times zeta n minus the term zeta n plus n. That was the shuffle. And the shuffle looks a bit more complicated. So you choose, say, R and J, choose R and the complement of J in K, and subtract 1 everywhere. Okay. And then you multiply with zeta R times K minus R. And that's equal to zeta I times zeta j times zeta complement of j.
The first relation is kind of elementary, I guess.
That's immediate, just looking
Yeah.
at the decomposition of the square, of the quadrant, into an upper cone, lower cone, and the diagonal. So that's one cone, that's the other cone, that's the diagonal, and that's the product. But here that's more complicated. You have to pass through to a different alphabet, like the passage from some notation of zetas, multiple zetas, to the integral. There you have differential forms, one forms, that can be encoded by 0 and 1 only, and you shuffle those. You shuffle words in just two letters, and that's what comes about. And that's essentially what comes out here. So R from 2 to k minus 1, I think that's then a relation. Okay, so we can make now an ansatz. Instead of looking at these numbers, these real numbers, work with formal double zetas. So then let's have a symbol ZRS that replaces zeta R comma S. So that's our formal symbol. Then we have a symbol for the product, PRS, corresponds to zeta R times zeta S. And then also a single indexed Z, which corresponds to zeta K. And then you rewrite 1 and 2 in terms of Zs. So maybe I can do that, you cannot. So here we take Z R K minus R, here we take P J K minus J, and so on. So here P and N.
Zeta V times what is V?
Did I do something wrong?
Is it P?
P
Click on line. Zeta J times zeta K minus J.
K minus J.
Yes. Z J times Z K minus J. I'm sorry. Asking.
Right. So if it's a product, we replace it by the P variable, and if it's a genuine double zeta, then by a Z variable. So Z and N plus Z and N equals that minus ZK. Okay. So that will be our system with which to work, and we can even allow a formal Z1K minus 1. That would play the role of the divergent zeta 1 comma K minus 1. But in the formal context, nothing blocks us, obviously. Okay, and then we define the formal double zeta space as the collection of symbols, or Q vector space generated by those symbols divided by the relations that we have given. And I emphasize that this is not the full set of relations, right? It's not the regularized version. Right? We expect that the regularized one gives us everything, but here we have sort of a restricted setting.
So there's no relation involving Z1K minus 1.
Oh, there is, but
I mean the divergent one.
yeah, we take with then you also need Z1.
Then
But
So for example, take the very first relation there. Zn plus Zn. Are you going to allow?
you have to allow Z1.
And that's the and that formula then is.
Then that also follows, yeah. That's a formal thing. But okay, I won't do that. So let's forget about it. I forgot a bit about what the consequence was. Before I say something stupid, maybe I just ignore it. I just say the formal setting has the virtue that you can work with more symbols, and you don't have to worry about divergence here. Let's define the formal double zeta space. Here's the Q vector space spanned by, let's give it a name, dk. Those symbols, 0s, prs, and zk, with the weight all the same, being k. For now, I do allow the z 1k minus 1, where 1 and 2 are satisfied. So divide by those relations in the formal setting. And so now we can work with by comparing the two, we see that we can eliminate pj k minus j by taking the difference. So we just take the double zetas and zk and divide by sort of 1 minus 2. But I think obvious what I mean by that. So you eliminate PRS. And that has the virtue of making dimension counts a bit easier. In particular, we immediately see that the dimension of the resulting space is bounded from below. So the dimension of k greater or equal to k over 2. So the second one gives by symmetry you only need half of the j, therefore that's essentially only have k or half relations.
And why don't you implement like zk times the s is PRS?
It's a useful construct because later on we will try to only give us PRSs and hope to lift it to the ZRSs. It makes it easier than to always flap around the ZRS plus ZSR. Right, that would be minus ZK even, so it makes it a bit more cumbersome. It's for convenience. No.
It does make the equations homogeneous, but that's right.
Okay, just maybe to indicate a proof of that refined sum formula. Proof indication of refined sum formula. Just work with generating functions. And the crucial thing here is to find the right objects to use. Here it is. So, take the ZRSs, and you don't take x to the r, y to the s. That would be sort of the first instinct, but rather it turns out that the right thing to use is the r minus 1 s to the y to the s minus 1. And then 1 minus 2 becomes a 4-term equation in the zk's. Reasonably simple, so that I can still write it up. So x plus y, comma y, plus the zk, currently zk x plus y, and you subtract zk times y, and you subtract another zk, but this time the other way around, yx. And this is slightly more cumbersome, zk times a polynomial xk minus 1 y to the k minus 1 over x minus y. And then now you simply put x, y, specialize to the 1, 0 and 1 minus 1. And subtract or add the resulting expressions. And let's subtract.
X and Y commute. X and Y are commutative parameters.
Yes. Mm-hmm. Yeah. So this is not the non-commutative situation. But I have a hunch that maybe this is sort of a shadow of a non-commutative thing. That's what I indicated just an hour earlier. Okay, so that's an indication of proof of 1 and 2. By specializing those two and manipulating, you immediately get simple relations. Okay, so that's.
So I'm covering that formula
Ah, sorry.
ZK.
ZK times sort of a cyclotomic expression, sort of the x to the k minus 1 minus y to the k minus 1 divided by x minus y. Okay, so then the theorem that I just mentioned for k greater or equal to, let's say, greater to even on the safe side, the z odd form the basis of the double zeta space dk. So you only need, right, we have z odd odds and z even evens. So we can express all the z even evens in terms of z odds. And I could give maybe the formula if, well, we've had maybe enough formulas so that you're saturated. So the formula involves Bernoulli numbers and binomial coefficients and products thereof. So it's already a bit unwieldy. So maybe I'll leave it for now, because otherwise I won't get to the point anyway. Okay, and as a corollary, we get that the dimension of dk is equal to k over 2. We had already bound from below. Now we have, we say a basis. That gives us indeed a dimension equal to k over 2. And what I just already indicated, if we take an even expression in zeta in z, there's a sum of rational times that odd odds. So for fixed weight, obviously always and similar for p even like that. Now,
Simon,
yep.
I thought your conjecture of the dk involved modular forms for k even.
So far, we are not yet at modular forms.
No, I know, but I mean, I thought the conjecture was not k over 2, it was k over 2 minus.
Right, for the real zetas. But here we're in the formal context.
Oh, okay.
Now we'd like to go to the real context, and we must somehow see the modular forms. Right? So if we first go to the setting where everything is in order, and then by taking the quotient, by the right thing, we'd like to retrieve the situation for the reals.
But you're not saying that you're missing relations by thinking of the double shuffle, because that's really
Interesting.
But you seem
Well,
to be
that's
saying
one
that-
thing. That's one thing.
But
But-
you seem to be saying that double shuffle is not enough to recover everything.
Yeah, first of all, we only take double shuffle without the regularization.
Okay, that's
Regularization.
regularization which is missing.
Yeah, but even in this world, we don't see all the Euler relations, like zeta 4 equals zeta 2 squared, or zeta 2k is.
You don't see all consequences of
You don't
double
see
shuffle.
all of them.
Okay.
You see partial information, but not all. And that's a strange thing. And the reason somehow is modular forms coming in. Okay. So we can try to characterize relations among those double zetas. So the proof of uses characterization of formal double zeta values, value relations in terms of polynomial. And I give a template expression. So let's call that, for some reason I have double star, I've glossed over a star. So some ARS, ZRS is lambda zk in that space, dk. So these are rational numbers, obviously. So with those, okay, ARS and lambda and q. If and only if the following polynomial has special property. You take k minus 2, choose r minus 1 times the same coefficients ARS. You multiply by x to the r minus 1, y to the s minus 1. And you write it as the difference of x plus y minus h of xy for some polynomial h which has a special property. Yeah. It's symmetric. Symmetric, homogeneous polynomial h of degree 2 variables of degree k minus 2, k still being the weight. So relations among formal double zetas are now translated into the corresponding polynomial expression with its coefficients, these ARS, are given by a polynomial with a certain property. And one can lambda, which is sort of expressed in terms of h, as something like k minus 1 over 2 and an integral ht 1 minus t, so kind of gamma or beta integral. Okay, but that's sort of aside the whole thing. And one also uses now, once you have given your ARS for all even ones, so sum k, as I indicated earlier, this allows to reconstruct a whole collection, to complete it to a collection of numbers AR, S, and lambda, satisfying the whole equation. This equation double sum. So we only need to know what it is on the even ones, and then suddenly we can reconstruct. Okay, so that's and it uses manipulations in the group ring. Use clever manipulations, and one of the heroes in this game again is Zagier. In the group ring Z PSL2 Z. So there you see sort of implicitly already modular forms here, and they act on the space of those polynomials. Okay, so all we need to take with us, I think, essentially, so double zeta relations have been expressed in terms of polynomials. Now we'd like to see polynomials in terms of modular forms. So that's the other side, and then relate the two. So I'm not sure whether you've seen modular forms before. So I give a rough idea, even at the peril of boring most of you. So functions from the upper half plane to the complex plane with infinitely many symmetries. So that's maybe in first approximation. So you have a huge group of symmetries, PSL2Z essentially. So more precisely, so F, if you apply sort of a matrix A, B, C, D to a vector Z1, where Z is in the upper half plane, I called it H, double H, the upper half plane. So this is X plus I, Y equal to 0, just to fix notations. So this is simply a Möbius, you think it represents a Möbius transformation, AZ plus B over CZ plus D. This is the same as F of Z up to something. Right? So that's sort of the symmetry that I'm saying for all A, B, C, D in S or PSL, say SL2Z. The P is a minor annoyance. So you get a prefactor in terms of the sort of denominator of this expression, and this has a power typically. That's the K of the weights that we looked at a bit earlier. So it's the same K, so we should really identify this K with the weight for multiple zeta, so consistent. And you can check that actually for two generators of PSL2 of order 2 and infinity, or in fact you can even do that for order 2 and order 3. Let's not do that. So obviously, modular forms play an important role in many number theoretic contexts, but just as a basic thing. And maybe one can give examples, quick examples. Eisenstein series, if you have never seen those before, just sum over a lattice. You take away the point 0, 0, but then essentially you say m tau plus n, and you raise it to power k. So that gives an interesting function, and so the tau in the half plane.
Yeah.
And
So you said m and n are equal to 0, 0.
Oh! Okay, so that's, and to check modularity, it suffices to check with, well, two symmetries. Then there are theta series, which for a quadratic form on some space f to the r, you just sum over that quadratic form essentially. So in the following way, you take n, maybe I should write vector, and take the quadratic form of that R tuple and have q raised to that power, and that's called the q of tau, where q equals is an expression in terms of tau. The standard convention is q is e to the 2 pi tau. So these are important, and their coefficients play an important role in numbers of ways writing a given number. Jacobi, sum of squares, for instance. Then we have a discriminant function, which is, for instance, given by product expansion. So you have an infinite product. So where n goes to 1. Again with q, that expression, and that has a nice Fourier series for expansion. So it's q plus I think 24 q squared plus higher ones. So it has no constant coefficient, and that will be sort of the defining property of a cusp form for this L2. So you always have Fourier expansion around the point infinity, and that implies, and the Fourier coefficients typically have interesting number theoretic interpretation. And the last one, maybe, in case you haven't seen that, so called the J function. So this is up to multiple. I haven't given you the multiple e4 of tau cubed divided by delta of tau, and that's up to a multiple 2 inverse plus 744 plus, and then you have 196,884 or 3, no, 4 plus 21493760 q squared. And those numbers play a role in counting dimensions of the irreducible representations of the monster group. Monster group dimensions of irreducible representations. So the smallest non-trivial one has the order 96,883, and adding it to the trivial one, that gives you that term, and the next one has this big number minus that minus 1. That's the dimension of the next one, and similarly. So it's lots of connections. That's all. Okay, all I want to say. And what we're actually interested in is in the fingerprint of modular forms. And that's very telling, and it comes about as a kind of moment of the modular forms.
J is the modular form.
J is not quite, well, it's an, it's actually, it's a modular, it's not holomorphic. So typically, so that should be holomorphic, F, not just function, if one is precise, and it should have a certain boundary condition, a certain growth condition at infinity, which I've all swept under the rug. This is a modular function, in fact, so it has its modular form of weight 0, but it's not holomorphic. So it has, as it starts with Q inverse, so there's a problem there. But it's a very important one. All the modular functions in weight 0 can be expressed in terms of that. So it's a rather basic function. Okay, fingerprint. The numbers, and I think one can roughly think of them as moments attached to f tau, say for a given f modular form. And now, in order to make sense, I really need, I think, holomorphic and the growth condition. So then you just have tau to some, call it r, tau, and we integrate along the imaginary axis. So that's what we do. We'll for r from 1 to k minus 1. That's somehow the crucial interval. Actually, from 0 to k is the crucial one, but 0k are a bit special. So
K is the weight.
K is the weight, still the weight. Yeah, let's do that. F modular form of weight k. And then we take this, the collection of these numbers.
Q out from 1 to k minus 1, in the case the power should be r minus 1.
Yeah.
How about it?
Is there? You mean here the power should be r minus 1?
R minus 1.
Yes. Good point.
What?
So I want to see it this way. Sorry. Yeah. I'll spot it. Yeah, one actually has tau to the r d tau over tau. I think that's the maybe better expression. And this is essentially what one calls L values of f in the critical strip. That sort of indicates critical strip. But don't worry, that's just distinguished one. And the problem, or the property, is so these numbers. I said the numbers, blah blah blah. Certain L values, that's making emphasis, are of the, I should give them a name, maybe, okay, I'll call them maybe L, although that's not quite dot. So it's not exactly what one usually says, L, but for me, let's do that. Are proportional over Q if R congruent to R prime mod 2. So two different of these numbers are, the quotient of these is a rational number if the difference is an even number. That's I think a not so trivial result. And therefore it gives rise to two distinguished rational polynomials, one for the even ones and one for the odd ones. Okay, so gives rise to two rational polynomials. So you divide out by the presumably transcendental content, like the first non-zero L value in that sequence of equally spaced indices. So of same parity, I already said that, sorry, stupid. Rational proportion gives rise to two polynomials, even slash odd. And amazingly simple characterization of modular forms, I think. At least for the case that we're only interested in, SL2Z. Those polynomials are characterized by a single functional equation, single condition. So classically with two conditions, a twofold and a threefold condition, twofold and threefold symmetry, but one can make it better and just write it as a single condition. You take a polynomial pxy and you decompose into two by writing the first one as the sum or the second one as the sum and leave the other one in place. It's that simple.
How did P come from the modular form?
No, the P is now a polynomial. So to two polynomials, say P.
One variable.
Here.
It's not clear. So you say there's some numbers and then
That's right. That's right. So
yeah, follow, yeah.
good point. We have a homogeneous polynomial in two variables. So yeah, we take those so homogeneous in xy of degree k minus 2.
I mean, so
Whether-
they're made up of these alpha.
Of these
so-
LFs.
Yeah,
But you choose them sort of
It's not
for the
very
even
formal.
ones.
Yeah.
Yeah, essentially, so it's essentially sum LFR are even, x to the r, y to the k minus 2 minus r. And then you divide by the first non-trivial one, so to make it rational. Right? Because all of them, you know, by that theorem, are related rationally. And the other one is or odd.
I see.
So these are the two rational polynomials that we associate. And they happen to satisfy this relation and are characterized by it, at least if k is greater 2. So for k equals 2, that is a slight ambiguity. But we're not interested in that case anyway. So a single one, and
So
sometimes.
if you have one satisfy such relations, the coefficients must be these LFRs for some
Yeah.
modular form.
Well,
Yeah.
up to a common multiple.
Up to a common multiple. Yeah.
Yeah. So if it, and I think that's quite surprising. Sometimes this is called, I think, Lewis equation, or it's some avatar of what's called the Lewis equation. So a three-term functional equation, which plays a big role in modular forms theory. I think when Manin originally, so it was Shimura, Aiko Shimura found that connection with sort of representing modular forms by those integrals, and therefore found a space of the space of modular forms into some polynomial space. And Manin figured out, I think, that the I'm not sure exactly what so I shouldn't say anything because you know much better what probably. Okay, but altogether they gave us this beautiful characterization of modular forms in terms of polynomials, and it's really very telling. It captures essentially all information of the modular form to an extent. At least you can reconstruct a lot. And yeah, what do you want to say? So we put WK, so it's all P in, VK I didn't introduce. So VK, this is the space, Q space, rational Q times X to the R, Y to the K minus 2 minus R. R from 0 to K minus 2. Right, we just take the vector space spanned by those monomials. So it's just the
that is the old relation. Or is it X symmetric on X and Y?
that's the previous relation So you can rephrase it with two equations. So a two-term and a three-term relation. But it's simpler, or even, maybe even better, to just rephrase it into a single one. So I think that's Zaghi worked a lot on this too, because he originally had played around with the two equations, with the two symmetries. I think these are the classical ones, probably by either Shimura or maybe that's what Mani added. And now you can replace it by a single one. So you take all those p satisfying this extra relation. And that's your space WK. And then the involution exchanging x and y splits this, so it decomposes into plus and minus eigenspaces.
What's Q?
Q is in Q, sorry, yeah. I'm stupid, yeah, I already have the Q. So it's just generated by all the monomials with a, how should I say it? It's homogeneous polynomials of degree k minus 2 over q, nothing else. Just
period polynomial is Q coefficient.
with q coefficients.
The value.
Yeah, maybe.
So C.
I think yeah. The convention is maybe like that. What? No, it's not. No, it's the span. This q span. No, that's not what we're sorry.
Coefficient is C, no? Q coefficient.
No, we want q coefficient because we know that if you take every second one, they're rationally related. And that's how you get a Q structure. You want a Q structure. I mean, the L values are certainly, or almost certainly not in Q. Therefore, a priori we're in C, but you divide by the first non-trivial one, and then the quotient. Everything is a rational multiple of the main one.
So you say it's a deep theorem that these quotients are rational?
I think this is not completely obvious, yeah. Certainly not to me. Like if Zaki were around, he would tell.
I'm sure this is not obvious. It's not to me. Yeah.
But here, the W is a subspace of.
Yes.
This is so VK. So I said VK. So this was sorry. Good point. Yeah. Because I didn't introduce V earlier, so I wanted to do it here. So WK is a subspace, absolutely, in here, of VK. And we can give the precise dimension roughly half. And the involution XY now decomposes into plus and minus minus 1 eigenspaces. And this suggests to take just one of those. And we call those plus WK minus, plus and minus, for plus and minus eigenspace. Okay, and the famous theorem, the characterization that I mentioned, due to Shimura, and Manu was also involved. It tells you that WK plus equals isomorphic to the space of special modular forms called cusp forms. And the S is for the German word Spitzen form, which is Spitze is a cusp, so that's where the S came from. And WK is isomorphic to space of modular forms of weight K.
So you mean SK means the all Fourier coefficient is rational number, right?
That's not necessarily, but the Fourier coefficient, the constant Fourier coefficient is 0. Cusp form means constant Fourier.
SK is a Q vector space, right?
Yeah.
Yeah.
So typically that's a Q vector space, at least for SO2Z. So I should say SO2. And there everything, so the Fourier expansion gives you everything in terms of, has a pure structure. So constant Fourier, constant in Fourier expansion equals 0. So modular form is allowed to start with anything. So it's just one dimension larger. Modular forms. All modular forms. And one essentially has mk is sk plus the Eisenstein series that I mentioned, so the space q times to be more precise. So here one takes a q structure, here we take that, or maybe it's easier to say that over C to be on the safe side. But roughly, that's that. So cusp forms are not far away from the whole set of modular forms. Essentially, it's just this Eisenstein series which plays a special role. And so these two spaces are not far apart anyway.
But didn't you say they have the same dimension? More or less?
More or less, yeah. Up to 1.
Oh, I see.
So there's just one, so the dimension
Dimension
UK
minus-
is dimension sk plus 1.
Okay.
So you can pass from one to the other, and cusp forms are a bit easier to handle in the period polynomial context. Because when you want to, in terms of these polynomials, if you want to add the Eisenstein series, you encounter 1 over x, which you don't really want to deal with a priori, but you have to go away from polynomials. That
So
makes it a
the
bit.
cusp form they lie in both spaces, but encoded in different ways.
Yes. And so one can try to find modular forms in both spaces. And then the zeta values that we are aiming at. And theorems, that's, why did I say 3, whatever. So in our paper, like here, find there is a canonical isomorphism from WK minus well, it's certainly WK minus to space of even evens divided by the induced relations among those generators only in dk. So dk is generated by zkr, pkr, and zk, but if we only take the p even evens, then they inherit a number of relations. And if we take that quotient, these are isomorphic, but a better statement. And that's how I would like to indicate the connection is as follows. So more precisely, for each modular form, the weight k, obviously, produce an explicit relation among z on-ons and p even. And in weight k, and here the weight is model zeta weight. And just to give the recipe, it shows that it's still far from, I think, really understood. So suppose you have p, I'll take small p for some reason, in WK minus. Then what you do is you write qxy, which is essentially p of x plus y, y. So you expand it again, and you find coefficients QRS to the r minus 1, y to the s minus 1. And here we have binomial coefficients. Okay, k minus 2 over r minus 1, I think. Seems so. Then, what happens is that there is, if we take these QRS now, we took from our element P in the satisfying period, or there's this special condition that I mentioned, the triple star condition, from which we made the QRS. Among those, we find the following almost equations. So it's the sum for QRS. On the left-hand side, we have the double zetas. On the right-hand side, we have the products. On the left-hand side, we have even r's. On the right-hand side, we have odds. And the congruence is mod zk. So we sort of ignore the coefficient of zeta k at this stage. But starting from an element in here, you get a relationship relating the ZRSs for even ones with the products of PRSs on. And maybe to see how that gives a relation in a specific case, you may remember what Leila wrote as an interesting combination originally occurring in Ihara's work. So what do we... Okay, I'd like to retrieve that one. So we call Ihara's relation as in Leila's talks, and the way she phrased it. She said something, you have a Poisson bracket on this Lie algebra, and then if you write 9,3, so she had, I think, F9, F3, or was it S? I think S is maybe, I forget. Minus 3 times S7, S5 is 0 mod 691. With this special and strange relation that she mentioned for the setting of the Lie algebra setting. And so we have coefficients 1 and minus 3, and I'd like to indicate how to retrieve those from period polynomials here, how they are related. And so that corresponds to an element in weight 12, and so we have in weight 12 minus, we have x squared minus y squared cubed. So if we interchange x and y, we indeed get a minus sign because we have power 3. Then I claim that corresponding, that is our pxy. Then you get qxy as the px plus yy as, okay, what do we have? To the 8y squared plus 8. So I just give the coefficients 1, 8, 25, 38, 28, and 8. This is coefficient of x to the 8y squared, to the 7y cubed, and so on. Okay, and you can write that as up to a common factor, 1260, as 28 times, divide by, times, which way around, 84 times 10 over 7, 150 times 10 to 6, 190, 10 to the 5, 168. And choose 4, and just 2 more, the last one being 0 anyway. And then you read off what is it? Every second one. So this one, that one, and that one. And these will give you 28 zeta 93 plus 150 zeta of 75, 168 zeta of 57, and it will be up to zeta k, will be 28. You can read off the what is it? No, 84. Here we have 84. That would be shit. I should do it in the formal world. Everything's formal. So it's Z93, Z75, Z57. Here we have 84 corresponding to P84. 190 divided by a third, I forgot, times P66, and a third 84 P, not P, Z, Z48, and those combine. Okay, maybe one or two things up. I just wanted to indicate the idea. And then you read off the relation in the real world. You know that all these, so that corresponds to P84 if we put those together. That is a rational multiple of a power of pi. The middle one is a rational power of pi, so that is those 75 plus 168 zeta 57 is something rational multiple times zeta 12. Just I think I messed it up pretty much, but so rough idea. You start with a period polynomial up there. This is the one where you see actually if you expand 1 and minus 3. Maybe I should have done that. Right, so this is x squared y to the 8 minus 3 times x to the 4 y to the 6 plus 3 times x to the 6 y to the 4 minus x to the 8 y squared. And here are the 1 and 3's. That's a 1, that's a 3, minus 3. And with that procedure, so essentially you just make a variable transformation x and x plus y and take binomial coefficients at the right place. That's all you need to figure out a relation among double zetas which arises from modular forms. So relation among double zetas from modular forms, arising from modular forms. And this was sort of the first instance of such a relation that I found, and it was instigated by a question that Terasoma gave me when we shared an office at Max Planck at the time. He asked, are there any relations among these zeta odd odds? Because somehow the question was, do these maybe form a good basis for that, but it doesn't seem so, because there are these spurious relations, and that triggered then further investigations into the topic. So I think maybe So all I wanted to indicate is, at least on one level, is how to make a connection between modular forms, for which you can write down these period polynomials reasonably easily, and immediately find a relation among the double zetas, which has a particular meaning in this context. So one can try to now interpret this further, and in the context of a refined dimension conjecture by Grothendieck-Teichmüller. So instead of so far we had seen 1 over 1 minus x squared minus x cubed. In other words, Xavier's dimension formula. Grothendieck-Teichmüller suggested that you can also refine it sort of respecting depth. So you add a second variable, you find maybe we call bkxy as the following power series. So let's make it simple. So this is the interpretation of. Okay, maybe I'll just write the. No. O of x times y plus s of x. I'll say in a minute what that's supposed to be. So that's a reinterpretation of their original formula, which looked a bit ad hoc in Haracanico Xavier, where they try to make sense. They have a numerator which is not important for us. But this indicates O of x is x cubed divided by 1 minus x squared. So this counts, so this is x cubed plus x to the 5, so all the ones. So this counts the dimension of what we expect the algebra to have. So one odd, what is the right context? One generator in odd dimension.
The last term of the denominator, is it?
X to the 4. Thank you. Yeah, so that's important. And okay, what's the interpretation? So, the 1 over 1 minus O of x y somehow gives you dimension of algebra generated by depth 1 generators. Now, if you sort of add a term, s times s of x, whatever that s is, I'll write it down in a second, y squared, that takes away dimensions in depth 2, and this is simply given by x to the 12, 1 minus x to the 4, 1 minus x to the 6, and that counts the dimension of the cave grading of Z2. Is that? And now in the fourth step, or in the third one, you add this one, but now you plug it in again in depth 4. plus s of x y squared minus s of x y to the 4th means add this back in depth 4. So, okay, we have something generated in odd greater or equal to 3 weight. So that's in depth 1. Then we subtract, we have extra relation, that's from what it says, in depth 2. These correspond to the relations that we've seen here. They somehow are encoded in such a dimension count, and then they are plugged in again in depth 4. And that's a rather strange behavior, but that seems to be valid, at least up to weight, say 35, I think that's what they checked with the data mine. And people have tried to interpret this. So with Leila and Sarah, we have tried to give an interpretation using a special filtration, a special depth filtration on that space, underlying space. And for instance, Brian also has an interpretation, more conceptual maybe in terms of cohomology, that may give an idea how to reinterpret those finer dimension conjectures. So just to story goes on. So modular forms are not just in depth 2, that was the topic of the talk, but in fact they propagate somehow and they push everything into depth 4 for some reason, and how they really appear in depth 4 I think is not completely known, but that's roughly what I want to say. Sorry for the confusion.
Is there any short question?
Yeah, if I specialize y to 1, shouldn't I get the formula above?
Almost. So here,
Okay, that's fine.
yeah, here, as I said, so there is a numerator,
Ah,
so which takes care of sort of the even dimensional, of the even weight parts. So q of zeta, if you view q of zeta as being 0, then you don't see that. Otherwise, I think you may get something like 1 minus x squared. Or something. Yeah.
So then the comment you made that if I subtract, if I get these relations among the in depths 2, then they have to reappear somewhere because the other formula, that's what I'm saying. If I specialize
Well,
y
something
equals 1,
has.
then something has to be subtracted. They have to reappear somewhere.
Yeah, but something has to reappear, but not the relation itself. Somehow an avatar of that relation
no,
in,
but I mean,
in depth
otherwise
4.
the formula doesn't work. I think this is also the question before. How do you reconcile this IGA's formula with the other one for depth 2 when you get these S relations? I'm just saying, if you specialize S equals 1 and you only add the term S of xy squared, then that won't do it. You have to have a second term which cancels it.
You mean if you just leave that?
If you just leave that and say that's
Yeah,
what you
then
have
it's
from
too small.
depth 2, then it doesn't work.
Hmm?
Right, exactly.
Yes, so that would give you some object that's too
So
small.
that's exactly what I'm
And
saying.
then you plug
so they
in.
have to reappear somewhere.
Yes. And so somehow those relations tunnel through and come back in depth 4, some strange reason. And I think that's not.
I'm not sure when you're speaking about the ERS relation, you mean the S9 and so on, there's a Poisson bracket.
That's right.
So a vague recollection that in quasi-modular form you also have some Poisson structure.
You mean Rankin-Cohen brackets,
exactly.
I guess?
So just is there any chance that this plays a role, or it's completely out of
I don't see it. I don't see a relation so far. There are too many structures among Rankin-Cohen brackets. They not only have Poisson, they have sort of the iterated things. I think 2 indices, but possibly if one finds.
A priori doesn't bring relation this structure, this Rankin-Cohen.
I don't think we can interpret those in terms of Rankin-Cohen. Maybe that would be a nice way to rephrase that in terms of Rankin-Cohen brackets for the right objects. Maybe that comes out. I mean, in the sense that I think Zaghi knows how to interpret Rankin-Cohen brackets, or these spaces WK, using Rankin-Cohen brackets. So maybe that helps. But,
So you should ask your question again next week.
well, if it comes up again.
Yeah. Zaki will come next week.
Yeah.
Any other question? Do you want to organize a discussion session in 30 minutes as usual, or?
I'm shattered as is, so.
Okay, what we usually do is this.
So
For those who are interested
Okay.
in long discussions with Herbert, but you know, people come and if there's no question, there's no question. So, okay, so let's see in 30 minutes.
Okay.
Okay, let's do it again.